I want to demonstrate to you that the period of oscillations, non-intuitive as that may be, is independent of the amplitude that I give the object. And I want to do that here with this air track. I have an object here. This object has a mass 186 plus or minus 1 gram. Call it M1. I'm going to oscillate it, and we're going to measure the period. But instead of measuring one period, I'm going to measure 10 periods, because that gives me a smaller uncertainty, a smaller relative error in my measurements. So I'm going to do it as an amplitude, which is 15 centimeters. Let's make it 20 centimeters. So I get 10t, I get a certain number, and I get an error, which is my reaction error, which is about a tenth of a second. That's about the reaction error that we all have, roughly. Then I will do it at 40 centimeters. We get a 10t, and we get, again, plus or minus 0.1 seconds. And we'll see how much they differ. They should be the same if this is an ideal spring within the uncertainty of my measurements. You see the timing there. I'm going to give it a 20 centimeter offset, which is here. And then I will start it when it comes back here. So I will allow it one oscillation first. That's easier for me to see it stand still when I start it. There we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What do we see? 15.16. 15.16 seconds. By the way, you can derive the spring constant from this now, because you know the mass and you know the time. Now I'm going to give it a displacement, an amplitude, which is twice as high. So I make it 40 centimeters. So this is 10, 40 centimeters, a huge displacement. Now, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 15.13. Fantastic agreement within the uncertainty of my measurements. In fact, they are within 300ths of a second. Of course, if you try it many times, you won't always get that close, because my reaction time is really not much better than a tenth of a second.